Hello, my name is Georgios Vavouliotis, and today I will be presenting a joint work named Exploiting Page Table Locality for Agile TLB Prefetching. This work aims at attenuating the Others translation performance bottleneck due to data accesses via TLB Prefetching, a pure microarchitectural technique that solely relies on the memory access patterns of the application and does not disrupt the existing virtual memory subsystem. Our solution to this problem consists of two modules. First, the sampling-based free TLB prefetching mechanism, or SBFP, a scheme that smartly exploits page table locality to enhance the performance of TLB prefetching by identifying the overall most useful free page table entries per page walk, and the Agile TLB Prefetcher, or ATP, a composite TLB prefetching scheme comprising three low-cost prefetch engines. In addition, ATP leverages adaptive selection and throttling mechanisms to enable the most appropriate TLB prefetcher per TLB miss, while disabling TLB prefetching when the TLB miss stream is irregular. Our evaluation shows that combining ATP with SBFP improves geomean performance by more than 10% across different benchmark suites and reduces the vast majority of the page walk memory references. Regarding the talk outline, first I will give some background information with respect to the research problem. Then I will describe the sampling-based free TLB prefetching mechanism and the Agile TLB Prefetcher, which are the two proposals of this work. Followingly, I will present the methodology that we used to evaluate our proposals and our experimental campaign. Finally, I will conclude my talk. In virtual memory systems, each memory access requires a translation from the virtual to the physical address space. Modern systems provide both software and hardware support to alleviate the address translation performance bottleneck. In this work, we focus on x86 architectural support for address translation, which is fundamentally similar to other architectures. On the software side, the page table stores the virtual physical mappings of all pages loaded to main memory. Most x86 architectures implement a 4-level radix tree page table. However, 5-level radix tree page tables are also supported today. On the hardware side, the memory management unit accelerates address translation through the translation Lookaside buffer, or TLB, a cache that stores the most recently used virtual to physical mappings, and the page structure caches that store entries from the intermediate levels of the radix tree page table to accelerate page walks by reducing the number of references to the memory hierarchy. Focusing on the TLB, modern architectures implement multi-level TLB hierarchies. It has been shown that last-level TLB misses account for the vast majority of the cycles spent in the TLB miss handler. Hence, from now on, I will simply use TLB to refer to the last level TLB unless stated otherwise. The TLB lookup lies on the critical path of accessing memory. On a TLB hit, the processor quickly obtains the corresponding translation. However, on a TLB miss, the page walk hardware is activated to fetch the translation from the page table, which implies multiple memory accesses. Therefore, page table walking incurs up to hundreds of extra cycles in penalty since performed in the critical path. To make matters worse, the advent of big data workloads has exacerbated the TLB pressure, resulting in large performance and energy penalties due to frequent page walks. Indeed, a recent reverse engineering study on different Intel microarchitectures revealed that TLB misses often cost more than 100 cycles, even in the presence of multi-level TLB hierarchies and page structure caches. Furthermore, our experiments indicate that the perfect last-level TLB would improve geomean performance up to 70% across different benchmark suites. The bottom line is that the address translation performance bottleneck is an emerging problem due to the tremendous pressure placed in the critical path by frequent page walks, especially for workloads with massive data footprints. Since our work focuses on TLB prefetching to attenuate the address translation performance bottleneck, now I will explain the operation of a system that incorporates a generic TLB prefetching scheme. TLB prefetchers typically use a prefetch queue to store the prefetched page table entries, since it has been shown that prefetching directly into the TLB has negative performance effects. On a memory access, we first check if the translation is already stored in the TLB. If yes, we return to the CPU. Otherwise, we check the prefetch queue for possible hits. On prefetch queue misses, a demand page walk is initiated to fetch the corresponding translation from the page table into the TLB. On prefetch queue hits, the page walk hardware is bypassed, and the translation is stored to the TLB and returned to the CPU. In either case of prefetch queue hit or miss, the prefetch logic is activated and produces new prefetch requests in the background. Note that each of these prefetch requests requires a prefetch page walk to store the corresponding page table entries into the prefetch queue. To elaborate on the way a page walk is performed in x86 architectures, let's assume a TLB MIS for a randomly selected virtual page. The bits of this virtual page are split into groups of bits in order to index the different levels of the radix tree page table. Each page table level access requires a reference to the memory hierarchy to find the corresponding pointer to the next level, which implies great latency and energy overheads. To motivate the sampling-based free TLB prefetching scheme, I will consider the previous schematic representation of a page walk to illustrate the locality in the last level of the radix tree page table. In x86 architectures, each page table entry is 8 bytes, and the cache line size is 64 bytes. Hence, at the end of each page walk, the page table entry that holds a demand translation is grouped with 7 neighboring page table entries, and they are transferred to the cache hierarchy. Therefore, at the end of each page walk, there are 7 page table entries that are prefetched for free. However, our analysis indicates that prefetching all these free page table entries into the limited size prefetch queue results in suboptimal performance gains, since it pollutes the prefetch queue with inaccurate prefetches. To address these findings, the sampling-based free TLB prefetching mechanism identifies and prefetches only the most useful free page table entries per page walk and adapts to phase-based behaviors, since it dynamically examines the usefulness of the corresponding free page table entries. Finally, SBFP can be combined with any TLB prefetching scheme to exploit page table locality for both demand and prefetch page walks. Before going into the core operation of SBFP, I need to provide some terminology background that is required for understanding its operation. As explained before, at the end of each page walk, the page table entry that holds the demand translation is grouped with 7 neighboring page table entries, and they are transferred into a cache line. We define free distance as the distance between the page table entry that holds the demand translation and another page table entry within the cache line. Therefore, there are 14 possible free distances, from -7 to +7, excluding 0. To elaborate on this, let's assume a TLB MIS for virtual page 83. At the end of the corresponding page walk, we first calculate the cache line position of the requested page table entry by extracting the 3 least significant bits of the corresponding virtual page. Then we can calculate the free distances of all the page table entries residing within the cache line. For example, the free distance of the page table entry of page A0 is -3. The SBFP scheme consists of 3 dedicated structures. First, the prefetch queue, a small buffer that stores the overall most useful free page table entries per page walk plus their corresponding free distances. Second, the sampler, another small buffer that stores the virtual page numbers and the free distances of the page table entries that are decided not to be placed in the prefetch queue. The decision of whether to place a free page table entry into the prefetch queue or in the sampler is taken by the free distance table, or FDT, a table composed of 14 saturating counters. Each counter is responsible for monitoring the usefulness of one free distance. Next, I will explain the core operation of SBFP with an example. At the end of a page walk for a randomly selected virtual page, we first compute the cache line position of the corresponding page table entry. Then we can calculate the free distances of all the page table entries residing within the same cache line, and we associate each free page table entry with an FDT counter. To determine whether a free page table entry has to be placed in the prefetch queue or in the sampler, we compare the FDT counter corresponding to its free distance with a threshold. If the counter exceeds the threshold, then the page table entry is stored in the prefetch queue. Otherwise, it is placed in the sampler. We follow the same procedure for all the free page table entries residing in the same cache line. On prefetch queue or sampler hits, we just increment the FDT counter corresponding to the free distance of the hit entry. Followingly, I will show that SBFP can be combined with any TLB prefetcher to exploit page table locality for both demand and prefetch page walks. To do so, I will explain the operation of a system that incorporates a generic TLB prefetching scheme as well as SBFP. On the memory access, we first check if the translation is already stored in the TLB. If yes, we return to the CPU. Otherwise, we check the prefetch queue for possible hits. On prefetch queue misses, a demand page walk is initiated to fetch the corresponding translation into the TLB. At the end of the corresponding page walk, SBFP exploits page table locality by storing the overall most useful free page table entries into the prefetch queue and the others into the sampler. In the background, we search for possible hits into the sampler, and if this is the case, we update the corresponding FDT counter. On prefetch queue hits, the page walk hardware is bypassed, and if the hit was produced by a free prefetch, we update the corresponding FDT counter. In either case of prefetch queue hit or miss, the prefetch logic is activated and produces new prefetch requests in the background. Each prefetch request requires a prefetch page walk to fetch the corresponding page table entry into the prefetch queue. At this point, SBFP is further activated to exploit page table locality for prefetch page walks by placing the overall most useful free page table entries into the prefetch queue and the others into the sampler. Next, we move on the second contribution of this work, the Agile TLB Prefetcher, or ATP. Our motivational analysis draws the following key findings. First, we found that there is no state-of-the-art TLB Prefetcher that performs best across all considered workloads. Second, we observed that different workloads correlate well with different features, which is the reason why there is no global best state-of-the-art TLB Prefetcher. And finally, we found that when the TLB MIS stream is irregular, state-of-the-art TLB Prefetchers continue to throw useless prefetch requests. ATP addresses all these findings. To do so, it combines 3 low-cost TLB prefetchers to correlate patterns with multiple features and introduces adaptive selection and throttling mechanisms to select the most appropriate TLB prefetcher per TLB MIS while disabling TLB prefetching when the TLB MIS stream is irregular. Next, we move on the constituent prefetchers of ATP. First, the Stride TLB Prefetcher, or STP. Assuming a TLB MIS for virtual page A, STP would prefetch the page table entries of pages A-2, A-1, A+1, and A+2. Second, the H2 Prefetcher, or H2P, a TLB prefetcher that correlates patterns with distances between virtual pages that produce TLB MISs. For example, let's assume that the TLB MIS stream is A, D, and E at a certain point in time. In this case, H2P would prefetch first the page table entry of page E plus the distance between pages E and D, and the page table entry of page E plus the distance between pages D and A. Finally, the modified arbitrary stride prefetcher, or MASP, an aggressive evolution of a state-of-the-art TLB prefetcher. MASP employs a prediction table which is indexed with a program counter that has 2 additional fields. First, the previous virtual page accessed by this PC and the corresponding stride. For example, let's assume a TLB MIS of virtual page A that hits in the prediction table of MASP. In this case, MASP will prefetch the page table entry of page A plus the corresponding stride, and also the page table entry of page A plus the distance between pages A and the page residing in the previous VPN field. The selection and the throttling schemes of ATP use 3 saturating counters that are responsible for selecting the most appropriate TLB prefetcher per TLB MIS while disabling TLB prefetching when the TLB MIS stream is irregular. In addition, ATP uses 3 fake prefetch queues, 1 per constituent prefetcher, which are responsible for monitoring the usefulness of the corresponding prefetchers and accordingly update the values of the saturating counters. Regarding the core operation of ATP, upon a TLB MIS, we first check for possible hits in the fake prefetch queues of all the constituent prefetchers. Depending on the search outcome, we update the values of the saturating counters, and then ATP leverages the updated values of the saturating counters to adapt its prefetching strategy. Specifically, if the most significant bit of counter C0 is 0, then ATP disables prefetching. Otherwise, C1 is probed to make the selection. Likewise, if the most significant bit of counter C1 is 1, then STP is selected. Otherwise, C2 is responsible for making the selection. Similarly, if the most significant bit of C2 is 1, MASP is selected. Otherwise, H2P is the one that is selected for the current TLB MIS. Regarding the simulation infrastructure, we use JumpSim, a trace-based multi-core out-of-order simulator, and we have incorporated in JumpSim an x86 page table worker, which was necessary for the purpose of this work. The simulated hardware configuration is shown in the following table. Most of interest is the 1.5K entry second-level TLB, similar to modern microarchitectures today, and the 64 entry prefetch queue, which is shared among the ATP and SBFP modules. To evaluate our proposals, we consider the entire SPEC 2006 and 2017 benchmark suites, industrial workloads provided by Qualcomm for the first contest on value prediction, graph processing workloads enclosed in the GAP benchmark suite and XSBench. We simply refer to GAP and XSBench workloads as big data workloads due to their massive data footprints. Finally, all traces have been obtained using the SymPoint methodology, and our evaluation considers only the workloads with more than 1 TLB MIS per kilo instructions. As comparison points, we consider the state-of-the-art data TLB prefetchers, the sequential prefetcher, the distance prefetcher, and the arbitrary stride prefetcher. To quantify the benefits of SBFP on TLB prefetching, we compare against the following scenarios. First, the no FP scenario does not store in the prefetch queue the free page table entries. Second, the naive FP scenario naively places all the free page table entries into the limited size prefetch queue for both demand and prefetch page walks. And finally, the static FP scenario uses the overall most useful free distances per TLB prefetcher. Following figure shows the performance results of the state-of-the-art and new TLB prefetchers when they are combined with no FP, naive FP, static FP, and SBFP schemes across all considered benchmark suites. First, we observe that all the TLB prefetchers achieve higher performance gains for all the scenarios that exploit free prefetching than when free prefetching is not exploited. We observe this behavior because free prefetches provide prefetch queue hits that save long latency demand page walks, and also most of the prefetch requests issued by the TLB prefetchers have been already prefetched for free, avoiding prefetch page walks. Furthermore, we observe that SBFP significantly outperforms the naive FP and the static FP scenarios across all evaluated TLB prefetchers. We observe such behavior because the naive FP scenario places in the limited size prefetch queue all the free page table entries for both demand and prefetch page walks, thus polluting the prefetch queue with inaccurate prefetches. And the static FP scenario does not use the free distances that are seldom beneficial in specific execution phases. Focusing on the ATP combined with SBFP, we observe that it provides the overall best performance results. Specifically, ATP coupled with SBFP improves geomean performance by 16.2, 11.1, and 11.8% for the Qualcomm, Spec, and Big Data workloads, respectively. To put these numbers into perspective, ATP coupled with SBFP outperforms the best state-of-the-art TLB prefetcher per benchmark suite by 8.7, 3.4, and 4.2% for the Qualcomm, Spec, and Big Data workloads, respectively. Followingly, we focus on the impact of TLB prefetching on the page walk memory references. The following figure shows the normalized number of memory references triggered by both demand and prefetch page walks across all scenarios in TLB prefetchers. The normalization factor is the total number of memory references for demand page walks without TLB prefetching. First, we observe a large increase in page walk memory references for the scenario that does not exploit page table locality. This happens because this scenario does not store the free page table entries into the prefetch queue, thus it misses the opportunity to save long latency demand page walks, and all the TLB prefetches require a prefetch page walk to fetch the corresponding page table entry into the prefetch queue, which implies multiple memory accesses. In addition, all techniques that exploit page table locality significantly reduce the number of page walk memory references, because the majority of the prefetches that require a prefetch page walk have been already prefetched for free, avoiding prefetch page walks, and the free prefetches provide prefetch queue hits that save long latency demand page walks. Finally, all considered TLB prefetchers experience their highest reduction in page walk memory references when they are combined with the SBFP scheme. This happens because SBFP saves more TLB misses than the other scenarios. Focusing on ATP combined with SBFP, we observe that it provides the overall highest reduction in page walk memory references across all workloads and TLB prefetchers. Specifically, ATP combined with SBFP reduces by 37, 26, and 5% the page walk memory references for the Qualcomm, Spec, and Big Data workloads, respectively. Regarding the storage overhead, ATP coupled with SBFP require almost 2 KB of additional storage. Our ISO storage evaluation reveals that our proposal outperforms the scenario that considers an enlarged second-level TLB by more than 9% across all evaluated benchmark suites. Therefore, we consider such storage overhead reasonable for a realistic design. Finally, you can find additional evaluation results in the paper. To conclude, this work is aimed at attenuating the Athens translation performance bottleneck due to data accesses via TLB prefetching, a pure microarchitectural technique that solely relies on the memory access patterns of the application and does not disrupt the existing virtual memory subsystem. Our solution to this emerging problem consists of two modules. First, the sampling-based free TLB prefetching mechanism, or SBFP, a scheme that can be combined with any TLB prefetcher to exploit page table locality by predicting the overall most useful free page table entries per page walk, and the Agile TLB Prefetcher, or ATP, a composite TLB prefetching scheme, which is comprised of 3 low-cost prefetch engines. In addition, ATP leverages adaptive selection and throttling mechanisms to enable the most appropriate TLB prefetcher per TLB miss, while disabling TLB prefetching when the TLB miss stream is irregular. Our evaluation shows that combining ATP with SBFP improves geomean performance by more than 10% across different benchmark suites and reduces the vast majority of the pagewalk memory references. And that's it with my presentation. Thank you very much for attending, and I hope that we meet physically soon.